Okay, so 2 or 3, and so the question then becomes: does the path have to go through the battery? Right? We can trace out one path that does go through the batteries. Let's say we start here, for example, and we go through battery number 1, and then we go through this wire. We go through battery number 2, and then we go through this wire. And then at this point, we can do what? Either one, right? So let's pick the top one, right? So let's go through the top one and go through here, and we're back to where we started from. So that's one loop, right? So there's one. And then we can do the same thing, go through the batteries and get to here, and then do what? Go down. Okay, so let's call that 2. And what's the third one? Around this loop, right? It does not have to go through the battery. We could pick a loop that goes through just those 2 light bulbs and their associated wires. So that would be loop 3. So in fact, there are 3 loop equations we could use with the loop rule. And let's actually write them out. We can just kind of reason out what the directions of the electric fields are. And by the way, what we often do in cases like this is that we looked last time, and we didn't get through the whole thing, but we asserted that, remember, we had a problem last time. We had a thick wire and a thin wire. And you guys ended up calculating the electric field in the thin wire, but we also said that in the thin wire, the electric field was, how did the electric field in the thin wire compare to the electric field in the thick wire in this circuit? It was bigger, right? And in fact, in what is often the case in situations like this, the electric field in these thin, what are called resistors, right? Thin resistive elements of the circuit, the electric field is so much larger that the field in the thick connecting copper wires, highly conductive wires, it's very small. It's almost negligible, so that the potential differences across these wires are very small. And you actually did an experiment like this, right? You worked out the potential differences across different parts of a circuit element, and you found that across the connecting wires, the voltages were tiny, right? Like 0.01 volts, 0.00 millivolt range. So I'm going to go through and just worry about the wires. And I'll say this is, I don't know, let's call this E1. So my notation is going to be a little bit different from the picture here, but that's okay. Let's call that electric field E1, that electric field E2, and that electric field E3. And we'll call the length of this thin, usually tungsten in a incandescent bulb, this thin wire, call that L1, call this length L2, and call this length L3. And then this is EMF and some EMF, and this is some EMF. So the total EMF would be 2 times that. Okay. So give me an equation. What's the first loop rule equation going to look like? Okay, I have an EMF, and it's actually 2 EMF, right, because there's 2 batteries. So 2 EMF, and I go through the top. Okay, what's the sign? Minus, right, because I'm going in the direction of that field. So minus E2L2, and then what? Minus E1L1, and then equal to 0. Okay. What's loop number 2 going to look like? 2MF minus E3L3 minus E1L1 equals 0. Okay. What about the third loop, the one that just goes through the bulbs? Yeah, okay, so let's pick a direction here. Let's say we're going, it doesn't matter, but let's say we're going in this direction. So we're going to go counterclockwise. So if I go counterclockwise through bulb number 3 here, I'm going opposite of the direction of the electric field, so that gives me a positive, right? So I have positive E3L3. But then if I go through here in the same direction as the electric field, that's a negative, right? So minus E2L2 equal to 0. Can I use those 3 equations to solve this system? There's 3 unknowns here, right? Electric field 1, electric field 2, electric field 3. Why not? One of the equations cancels out and we get the third one, right? These equations are not independent. If I you could do this. You could subtract this equation, sort of both sides from this one. The EMS would go away, E1L1 would go away, and you'd be left with this third equation. Okay, so if you can get the third equation from the first two, you don't have enough to solve the system. So what do we need? What else do we need in order to do this? Okay, well, if they gave us an answer, that would help, right? But where else can we get a equation from? What other rule can we use? Node rule, right? And how many different node rule equations are there?